And now let's look into our part C of example 1 here. And once again, this part of our example 1 utilizes the same beginning description. So pose rates generally have a known standard deviation of 4 BPM, beats per minute. A sample of 50 people gives a mean pose rate of 72.8 beats per minute. At significance level 0.001 is the sample of pose rate, showing strong evidence that generally mean pose rate should be greater than 72. And so again, after reading the description of our problem in example 1 part C here, we have to start into our first responsibility. In our first responsibility, we need to identify our two hypotheses. And so, one more time, quickly looking back at the wording of the problem, we want to prove that generally mean pose rate should be greater than 72 beats per minute. So, a little bit on scratch work here again, that mean pose rate, symbolically represented by the mu symbol because it's a population mean value. Mean pose rate generally greater than 72 BPM. So this statement right out of the wording in symbolic form is indicating that we're having an inequality statement. And so it can be perfect for using that as our alternative hypothesis. So in our hypothesis, H1, it says mu, the mean pose rate, is greater than 72 beats per minute. And once our alternative hypothesis has been identified, we can now easily find our H sub 0 by simply replacing this inequality in our H1 statement to be an equality symbol. So mu equals 72 is now going to become our null hypothesis. Similar arguments with how we have seen throughout part A and part B. Now this testing hypothesis, this testing procedure we are about to proceed is being regarded as a right tail test. And again, allow me to give the full complete explanation of what it means by being a right tail test at the end of this testing procedure when I'm done putting all the steps together and successfully come to that point where we can make a final answer, a final conclusion regarding whether or not our sample can be a strong evidence or not. But now, as far as the first step into the problem, the first step into testing our hypothesis, then we need to identify our sample value. And so again, back on the computer screen, the beginning of our question in part C says a sample of 25 people gives a mean pose rate of 72.8 BPM. That means we have a sample mean. This time, unlike the sample means we used for the first two example question, here our sample mean is switched to a different sample. So here we're looking at sample mean being 72.8 beats per minute. And this sample came out from a sample size of 50 people in our sample. Then after the first step, recognizing or identifying our sample mean value, then now we must realize that as soon as we pick one sample, or any time that we can pick one sample, then we must realize that this sample we have is not the only sample mean existing out there. There are infinitely many other sample means existing out there with the same sample size. And so in that way, the center or the average of all sample mean values in our problem here will be 72. This is the center of all sample mean values. So our own sample mean is here, but after considering all sample mean values, then all of them altogether come out to a center, an average of all sample means being 72. Allow me to wait until the end of our testing hypothesis problem here, where I have successfully put all the steps together and come to a final conclusion regarding strong evidence or not, to explain in full how and where this value of 72 came from. But now what we can see so far is that like the previous problems, then 72 right here comes out being consistent with the claimed value in our null hypothesis. And now, again, realizing that we have infinitely many sample means of size 50, and our sample is only one among the many sample means out there, then average spreading, or formally the standard deviation of all these sample mean values, symbolically we use that symbol sigma x bar. Sigma x bar in this case can be found by, again, look back into our problem, our computer screen. We already had a known standard deviation of 4 BPM. So this known standard deviation, once we had it given, we are going to divide that known standard deviation by the square root of our sample size, and in that way it gives us our value of the standard deviation of the sigma x bar value. Calculation comes out to be 0.57, and as I have explained in previous part of this video, that depending on different applications out there, you will run into different requirements, rounding requirements for the sigma x bar value. So watch out for different instruction on each little problems about how far you round. But generally, for the rest of the video here, I will always stay with 2 decimal places. And now, once we've had sigma x bar value, our sample, being one among the infinitely many samples, will have a z-score. Specifically, I call that z sub x bar here. So z-score, but the optional subscript x bar is to indicate that we're now about to find our z-score, the z-score for our sample means relative to the center of all sample mean values. So z-score is going to be, the math comes out 72.8 minus 72 divided by 0.57. So this is our sigma x bar value, and this is the center, the average of all sample mean values. Calculation can come out easily to be 1.40, and it's a positive 1.4 here. So that means our sample, from where it stands among infinitely many other sample means, it has a z-score positive 1.4, being above this center right here. And as a checkpoint for consistency, our z-score for the sample has a positive sign, indicating that being consistent with the fact that our alternative hypothesis is having an inequality that's pointing to the right. And further, our z-score being a positive value is consistent with the test procedure we're using here as being the right tail test. And now, for the next step, we are going to calculate a probability value. So among all sample means of size 50, I am looking for the probability where, in the events that we run into a sample mean greater than or equal. Again, to highlight that I'm using the right tail inequality here simply because our H1 hypothesis, our alternative hypothesis, is having an inequality that points to the right hand side. And further, this right tail inequality is to be consistent with what we have done, with what we have decided earlier, that our test procedure is a right tail test. And so now capital X bar 25, we're looking for capital X bar 25 to be greater than 72.8. And just like previous problems, 72.8 here being set up in our symbolic statements for the probability calculation. This value came out from our sample value. The answer to this probability problem here that we're looking at is being regarded as the p-value of our sample. And so now imagine that on a normal distribution of all sample means at size 50 in each sample, then 72.8 is somewhere on this bell curve, and this problem is graphically represented as an area shaded to the right hand side of 72.8 on our bell curve. But then proceeding further into actually calculating the value of this probability, then this probability should equal to the probability on the standard normal distribution curve, where z-score is greater than or equal to positive 1.4. And so now it's bringing us back, the problem is bringing us back to a calculation problem that can be done with the LS&D program. So we're just simply going to run our LS&D program, and when being asked for a z-score, we are going to provide a positive 1.4. But make sure the answer of this LS&D program must be subtracted from 1, because we are doing a right tail area, a right tail shaded area. So back on my computer screen again, with our z-score being 1.4. The area coming out from the LS&D program is 0.9192433. There's no need to round this answer yet because it's not our final p-value. So this answer from the LS&D program is the area shaded to the left of z-score 1.4 on the standard normal distribution curve. But this answer needs to be subtracted from 1, for what we're looking for here is being the right tail area, the area to the right hand side of a z-score. Final calculation shows that our p-value in this case is being 0.0808, and this is our final p-value. So unless being specified otherwise, usually any p-value I would go with 4 decimal places for rounding. And so now we are about to make our decision whether the sample that we've had can be regarded as a strong evidence or not. So with the p-value previously just now calculated 0.0808, we are going to compare with our significance level given in the problem. So let's again look at the computer screen here. But in this problem of part C, we are given a significance level of 0.001. And so in that way, comparing our p-value with the given significance level 0.001, this time our p-value is quite above the significance level. So in this way, the conclusion now says, so now having a p-value being above significance level, we can lead to a conclusion saying that our sample is not strong evidence. So, and it's not strong evidence to reject our null hypothesis h sub 0. Or you can also say it's not strong evidence to support our alternative hypothesis h1. And so, looking back at the question, ultimately the question is being written as a yes or no question, asking, is the sample of pose rates showing strong evidence? Just now we have concluded that our sample is not showing strong evidence. So the answer to the question this time is no. All right, so let's now look at the explanation on each of the steps that was done for our example 1 part C here. And also allow me to pick up from after we have already found our two hypotheses, because I have explained how to find these hypotheses so many times throughout the different videos. So all I need to do here is to briefly remind that in our part C of the example, then we had our null hypothesis stating that mu, the mean pose rate, was equal 72. And our alternative hypothesis was stating that generally it is suggested, or we want to prove that generally the mean pose rate should be above 72 beats per minute. And so back when I was showing the steps, then I was also indicating that right after identifying the two hypotheses, I was indicating that this problem we were about to do was to be a right tail test. However, here in this explanation of every step, allow me to save that explanation to the later part of this video right here. So I'm not going to be too worried about what kind of test this problem is for now. Our sample that we have already learned found to be 72.8, and this sample was at sample size 50. And so now, again, I have to emphasize, anytime we picked up a sample, then we must immediately realize that this sample we've had, provided that we add this, whichever sample size given here. But the sample value we have is not the only sample value. So in other words, this sample mean we have here is not the only sample mean existing out there. It is only one among infinitely many other sample means existing out there. So in that way, any of these sample mean values at given sample size 50 over here can generally be regarded as a random variable, capital X bar, and optionally I use a subscript 50. So capital X bar 50 right here represents the mean pulse rate in a sample of 50 people. And so at this point, it is important to understand that once we have defined this random variable here to represent the sample mean, the mean pulse rate in any sample of 50 people, then this is, in other words, an entire population of sample mean values. And so in that way, there will be a mean, a population mean of all sample mean values right here. And notationally, this is mu with a subscript X bar. And so central limit theorem that we have learned stated that mu X bar is always going to be equal to mu. And again, since we are having infinitely many sample mean values out there, and with mu X bar here as being the center of all sample mean values, then standard deviation of all sample mean values, understood as average spreading of all sample mean values, can be found by sigma divided by square root of the sample size. And so these are what we have learned from the central limit theorem. And so after a brief reminder about the center and the average spread on our sampling distribution of all sample means here, then here's how our logic of this testing hypothesis is being carried out. So after we have identified our null hypothesis, and recall again that a null hypothesis is making a claim that the value for pulse rate, the mean value for pulse rate is 72. So this value 72 right here is a claim value. And so the logic now is carried out as following. If for now we accept it, so I'm saying if h sub 0 was true, if we accept h sub 0 for now, that means we accept this claim value to be true, then consequently, according to the central limit theorem, mu x bar, which was stated to be equal to mu, and now we are accepting that mu equal 72 as in the claim. And so in that way, consequently, mu x bar must equal 72. And allow me to write this value in red ink right here. And now, as a further consequence, sigma x bar, the average spread of all sample mean values, can be found by, again, sigma divided by square root of n. But so let's have a look again at our wording of the problem here. In this problem, looking right at the beginning description, even before we started to read our part C of the problem, then there was a beginning description that remains permanently since even part A of the example. But pulse rates generally have a known standard deviation. So this known standard deviation, in other words, is independent with any other sample. Because at this point we have seen quite a few different samples already, and this standard deviation remains the same. And so we can use that value here to be our population sigma value, our population standard deviation value. So that means consequently, at this sample size we are using for each of our sample, then average spread on this sampling distribution of all sample mean values is going to be 4 divided by square root of 50. Final calculation of mine came out being 0.57. The actual calculation was a lot longer in decimals, but unless being specified otherwise, usually in any of my video lecture, sigma x bar is rounded to 2 decimal places. And so this mu x bar here is playing in the role of the center of the population of sample means. And this value sigma x bar that we have just now calculated is playing in the role of average spread of all sample mean values away from this center. Because recall again that sample mean values are being spread away, making some difference away from the center. And so this is on average, sample mean values are spread it by 0.57, or being different from the center by 0.57 on average. And that's why it's called average spread. And so now, once we have found the center and the average spread, and these are all consequences of accepting h sub 0, and as well as combined together with using our sample at sample size 50, then central limit theorem led to these consequences. And now again, realizing that our sample is not the only sample, but instead it is one among infinitely many other samples at the same sample size, then in that case, from where our sample mean value stands among infinitely many other sample means, then so 72.8, from where it stands right here relative to the center of all sample mean values. We're going to take a difference and divide the difference here between our sample mean with the center of all sample mean values and divide that by standard deviation sigma x bar. So 0.57 is going into the denominator. This work here is now giving us the z-score of our sample mean. So this is the work to calculate z-score, but I further use an optional subscript x bar here to indicate that this is not just any z-score out there, but this is the special z-score that is for our sample from where it stands being away from the center. And so now the calculation comes out to be positive 1.40. And yes, it is a positive value. And now on the other hand, let's look back at the wording description of our problem here. But right from the beginning description of our problem, besides this standard deviation, this known standard deviation given in the beginning description of our problem, then there was no further information regarding our beginning population, the population where we picked any of our samples from. My point here is to say that we did not know whether our beginning population was a normal distribution or not. But now, thankfully, that our sample size, currently being 50, is well above 30. Then, central limit theorem further guarantees for us that the sampling distribution, capital X bar 50, that we defined previously, is now normally distributed, or in other words, all sample mean values represented by this random variable capital X bar 50 are being on a bell curve. And that bell curve has center at 72 with standard deviation 0.57. And this is the reason why when it later came down to the step where we were calculating the p-value, which was set up as the probability that among all sample mean values of size 50, we're looking for the sample mean being greater than or equal 72.8. Then this calculation was calculated as a bell curve problem. Because we have just now proven that all sample mean values are on a bell curve. And so this bell curve has center at 72, and any values left and right of 72 is a sample mean value at size 50. And so this p-value calculation among our steps was done as a bell curve problem where 72.8, our sample is being somewhere to the right hand side of the bell curve center here, and this probability is graphically represented as the area shaded to the right hand side of our sample mean on the bell curve. So this value 72.8 is our sample mean somewhere to the right hand side of the bell curve, and the p-value set it up this way was calculated as a bell curve problem. And it was all due to the fact that we have just now proven that all sample mean values are on a bell curve, a normal distribution. And so once we realized that we can calculate the p-value here as a bell curve problem, then we proceeded further according to our steps that was showing earlier. Then this probability, or this shaded area on our bell curve here currently, is equal to the area on the standard normal distribution curve where we're looking for z-scores greater than or equal to 1.40. So this 1.40 was the z-score we have found for our particular sample. And this is why in the later steps, this calculation here can simply be done by running our LSND program And when the program was asking for a z-score, then we are going to enter 1.4, but make sure we subtract the answer of LSND program from 1, because LSND, as a reminder, only gives area shaded to the left of a value of a z-score on the standard normal distribution. But our area that we're looking for here on this bell curve is the area that's shaded to the right-hand side of our sample value. And so we must subtract the LSND answers from 1. So our final calculation came out in 4 decimal places, 0.0808. And now again, on the normal distribution bell curve that represents our sampling distribution of all sample mean values, capital X bar 50 in this case. This bell curve of ours had the center at 72. And just like any other bell curve, this bell curve also has a common area, a big fat area in the middle, right around the center. And outside of that big fat area, we have 2 little areas where I'm shading in red ink right here. One of them to the left and one of them is to the right. And these are being referred to as the unlikely areas. So back to the wording of our problem. We are given a significance level being 0.001 because it's set right here at significance level 0.001. So I have explained in previous videos that significance level notated as an alpha is how large this little right tail area is to the right hand side of the common area, and as well as how big that little area shaded in red to the left side of the common area. So that is our significance level. The red area, the unlikely red area, is our significance level in this case right here. And as a percentage, we have a 0.1% here and a 0.1% there on the left hand side. So that means the math can quickly lead us to the understanding that our common area in the middle here must be as big as 99.8%. And again, briefly, common area means those values found inside of this common area, those are the sample values that differ or fluctuated away from the center here, but commonly seen enough that we can accept. And this amount right here means we accepted up to 99.8% of sample values that fluctuated away from this claim right here. The reason we are allowed a common area is because anyone making a claim is in the end a human being, so human being can make error. And so if the samples falls inside the common area, then the person making the claim can just simply defend that, yes, even though it's different, but it's different within the commonly seen fluctuations. The sample found, even though being different, but as long as being in the common area, that means the sample is just one among those fluctuations that are commonly seen. So nothing's wrong with the claim. So from that argument on, our sample currently being 72.8, we already knew that this sample is to the right hand side of the center of the bell curve here, or in other words, our claim value. But we are further interested in finding out whether this sample would fall into that unlikely area outside of the common area or not. I will explain the reason why we are interested in finding out whether our sample would fall into the unlikely area outside of the common area in the later part of this video. But due to the fact that because we are determining whether our sample would fall into that right tail red area outside of the common area. This is again the reason why we refer to this test as a right tail test. And so now that I have given a detailed explanation of what it means by being a right tail test, but in the end, usually right after we have successfully identified our two hypotheses, the null hypothesis stating some claim value. So in this case, mu equal 72, and the alternative hypothesis was making some other statement that stating generally mu should be greater than 72. So just simply by looking at the alternative hypothesis that we have identified earlier, then that should be enough as a sign to indicate that our problem will be proceeded as a right tail test. And so my point now is just simply to say that even though I have given detailed explanation of what it really truly means a right tail test, but we can usually tell whether our test can be a right tail or a left tail test right by the moment that we have successfully identified our alternative hypothesis. And so now again, looking back at our p-value, our final p-value of our current sample was calculated to be 0.0808. And as a calculation setup, this p-value was set up as the probability that on our bell curve we would find a sample mean capital X bar 50 greater than or equal 72.8. And so on the picture of our bell curve right here, with the center at 72, then yes, 72.8 is somewhere to the right hand side of our claim from the null hypothesis, and the claim from the null hypothesis already became the center here. But this probability setup here is graphically the area shaded to the right hand side of our sample mean values on this bell curve. And then the comparison of our final p-value being 0.0808 with the significance level 0.001 now clearly shows that our p-value is well above the significance level. And so just now our p-value is being graphically represented by the black area shaded to the right hand side of our bell curve on this bell curve here to the right hand side of our sample mean. And I have explained earlier that 0.001 is the unlikely area outside of the common area. And in our particular problem here, it's the unlikely area in red that's to the right hand side of the common area. So now directly from this inequality, it's a straight comparison that simply our p-value is above 0.001. So that means if I would sketch our red unlikely area on this bell curve together with our shaded black area representing the p-value here, then here's how the picture is going to look like. My red unlikely area has to be smaller than, so here's my red unlikely area, and it must be smaller than the p-value being in black shaded area. And so in that way, it means in the way how the picture is representing it, that means the big the bigger area in black must push our sample to fall inside of the common area, because common area starts right from here and being inside, because only in this red area right here is our unlikely area. And so now, due to the fact that our black shaded area representing the p-value is to be already exceeding our red area, then the only way for that to happen is our sample, and just right on the picture is describing it, our sample must be falling anywhere inside of the common area. So that's just now proven that our sample mean x bar is among the common values. And that leads to a stronger statement that our sample mean value itself is a common value. And so now the importance of proving our sample mean value being a common value is that, yes, sample mean can differ from the claim here in the center, but what matters is whether our sample mean can be still within the commonly seen fluctuated sample means. And yes, it is. So that means nothing unlikely about our sample mean. Or in other words, nothing is wrong with our sample mean. Our sample mean, even though being different from the claim, but it's still being within the acceptable, commonly seen fluctuated sample mean value. So in other words, that's why we led to that that final conclusion, saying that our sample mean is not strong evidence, because it's still consistent, even though it's different from our sample here, but it's not far different enough. So in other words, people can still see that as it's still consistent with the claim whoever that person made right here. And so again, back to what I was halfway saying, x bar is not showing strong evidence, or itself is not strong evidence. And so not strong evidence here, either to reject h sub 0, because think about, if we want to reject h sub 0, the null hypothesis, then x bar better be strong evidence, but here it's not strong evidence for us to reject h sub 0. Or other way of saying that, x bar is not strong evidence for us to support. So there's not good enough reason to support h1, saying that generally it should be mean pose rate should be above 72. And so now back to the wording of the problem. In the end, ultimately, our question here of the testing hypothesis problem is a yes or no question. What it says is the sample of pose rates showing strong evidence? And so apparently just now we have proven that our sample is not showing strong evidence. And so the answer to that question I have highlighted is no. And so at this point, after seeing 3 examples, it's good to make some generalization here. So first, anytime our p-value falls below the significance level alpha, then this leads to our final conclusion about our sample as being strong evidence. Our sample is strong evidence. And otherwise, anytime that our calculated p-value is greater than or even sometimes equal to the significance level alpha, then that means our sample is not strong evidence. And that's how we generally make our conclusion regarding our sample. And as a further general understanding regarding testing a hypothesis that can be drawn after we've done example 1, 2, and 3 is that being a left tail test or being a right tail test, now at this point of our learning, after seeing all 3 examples, then we generally regard to either one of these, either a left tail test or a right tail test, as a general one tail test, simply because in part of the process we were interested in finding out whether or not our sample value would fall either into the left tail, the unlikely left tail outside of the common area, or fall into the unlikely area to the right of the common area, or we refer to that as the right tail test. So only one of the 2 cases happened throughout our 3 examples, 1, 2, and 3. And so in that way of my explanation, then the significance level in any of our problem in example 1, 2, and 3 is being generally regarded as the one tail or a one tail significance level. And so being a one tail significance level, it is the area outside of the common area. Okay, it's the area outside of the common area, but only on one side. And I have to open parentheses, either to the left or to the right tail. And so, as a graphical interpretation, with our significance level being notated as alpha, and now being a one-tail significance level, that means, graphically speaking, here's our common area on the bell curve. Any bell curve, then significance level is the amount, how big that little tail to the right-hand side outside of the common area, or here's another amount of being alpha, how big that area, that little tail area to the left being outside of our common area. So there's an alpha value here and there's an alpha value there, and that's what it means by being a one tail significance level.